Today we are here with the chapter 1 of physics class 10th, which is electricity. So let's begin this chapter. Let's talk about electric current. Let us consider a conductor AB which is connected to a cell or battery. The positive terminal of the cell is connected to the point A and the negative terminal of the cell is connected to the point B. So the electrons start to flow from the B to A, or we can say from negative terminal to the positive terminal. So the charge associated with these electrons with n number of electrons is Q is equal to Ne, and the direction of the flow of conventional current is opposite to the flow of electrons. So these charges, these negative charges or electrons, take some time to move from B to A. So let us consider, if the charge Q is flowing from B to A within time t, then the electric current flowing in this conductor will be given as this: I is equal to Q upon T, where Q is the charge flowing and T is the time taken. Here Q is divided by T. Whenever a quantity is divided by the time, it becomes the rate of that quantity. So this is the flow of charge and this is divided by time, so this becomes the rate of flow of charge. So we can say that the rate of flow of charge is equal to the electric current. Watch here, the rate of flow of charge is called electric current, and this is the expression for the electric current, the formula for the electric current, which is I is equal to Q upon T. Now the electric current is represented by I. The unit of electric current is coulomb per second. Watch here. The unit for this charge Q is coulomb and the unit for this time is second. So the unit of electric current will be coulomb per second, and this coulomb per second is also called ampere. So moving ahead with electric potential difference. So what is this? Let's discuss. Watch here. Here is a positive plate A, which is at higher potential, and a negative plate B, which is the lower potential. So the positive is higher potential and the negative is lower potential. Okay, if an electron is moving, a negative charge is moving from the point B to the point A, means from the lower potential to the higher potential, or we can say a positive charge can move from higher potential to the lower potential, from positive to the negative plate. Okay, so the charge, let us consider the charge Q is moving from B to A, which is an electron. An electron which is moving from the point B to the point A. An electron always move in the packets. A single electron is never ever moving. So we are taking the charge Q, which implies with the Ne, the n number of electrons, the charge Q which is moving from the lower potential to the higher potential, from the negative to the positive, between the points A and B. Then it requires some work done for the moving of the charge. Whenever a charge is moving from a plate to the another plate, from a point to the another point, it requires some work done. So if the work done to move a charge Q from one point to another is W, then the electric potential difference between those points A and B will be given as VA minus VB is equal to W upon Q. This VA minus VB is the electric potential difference, and this is the expression for the electric potential difference. So now we will define this electric potential difference with the help of this formula. Watch out. So VA minus VB is equal to W upon Q. Let's take this Q as 1. If Q is equal to 1, then VA minus VB is equal to W. This VA minus VB will be equal to W. Now we can read it. Watch here. The work done to move unit charge between 2 points is equal to the electric potential difference between those points. Watch here. The work done to move unit charge between 2 points is equal to the electric potential difference between those points. So this is the definition for the electric potential difference. Now let's talk about the unit. The unit of electric potential difference is joules per coulomb. Watch here. the unit of work done is joules, the unit of electric charge is coulomb. So the unit of electric potential difference becomes joules per coulomb, or this joules per coulomb is called volt. Now watch here. The flow of electric current takes place from higher potential to the lower potential. As we have discussed, the negative charge or the electrons move from lower potential to the higher potential. Watch here. This negative charge or the electron is moving from lower to the higher potential. The flow of electric current takes place from higher to the lower potential, means as the opposite direction to the flow of electrons. Electrons are flowing from lower to the higher, so the electric current will move from higher to the lower potential. Now let's talk about electric potential. What is this electric potential? Let's discuss. Okay, we have taken this point B. This point B we have taken to the infinity. At the infinity, the potential is 0. Okay, now watch here. This point A. At the point A, there is a charged particle where the electric potential is just V. The electric potential at the point B is 0. The electric potential at the point A is V. Now we are bringing a charge Q from B to the point A. Means we are bringing a charge Q from infinity to the point A. From infinity to the point of electric field. What is electric field? We will discuss it later. Now watch here. We have already discussed about the electric potential difference, which is VA minus VB is equal to W upon Q. Watch here. Here the potential at A is V. So put the value of VA as V. The potential at B is 0. So we will put the value of VB as 0. So watch here. VA as V, VB as 0, and W upon Q as it is. So what happens? We have V is equal to W upon Q. This is the expression for the electric potential. And why it happens? It happens when we take this point B to the infinity, where the electric potential is 0. So we will define this with the help of this formula. Watch here. V is equal to W upon Q. If we take this Q as 1, if Q is equal to 1, then V is equal to W. Now we will read it. The work done to move unit charge from infinity to the point of electric field is equal to the electric potential. So we can say the work done to bring the unit charge from infinity to the point of electric field is equal to the electric potential at that point. So we are moving or bringing the charge from infinity to the point of electric field, and to move a unit charge from infinity to the point of electric field, the work done, whatever the work done is, which is equal to the electric potential. So this is the definition. The work done to bring the unit charge from infinity to the point of electric field is equal to the electric potential at that point. Now what about the unit of this? Watch here. The unit of work done is joules, the unit of charge is coulomb, so the unit of electric potential becomes joules per coulomb or volt. Now let's talk about electric field. Watch here. Here we have a positive charge. Okay. Another negative charge is here outside the region about this positive charge. Another positive charge is there outside the region about this positive charge. These two charges are outside the region around this positive charge. But when these charges, this and this, come within the region, then they experience a kind of force of attraction or repulsion. In this condition, they are not experiencing any force because these negative and positive charges are outside the region of this positive charge. Now let's bring them in. When this negative charge comes within the region, then it experiences a kind of attraction force, and this positive charge, when comes within the region, experiences a kind of repulsive force. So when these charges are within the region around this charge, then they experience a kind of attraction or repulsion force. So we will say that this region as electric field. So let's define the region around a charge in which another charge experiences an electrostatic force of attraction or repulsion is called its electric field. So moving ahead, we will talk about the circuit diagram. So watch here, there are some electrical components. For them we have decided the symbols. So the electric cell is symbolized as this, a battery is the collection of cells symbolized as this, the resistor or resistance is symbolized as this. Now a variable resistor or rheostat is symbolized as this. An earth electrode is symbolized as this. Four connecting wires at a single point is represented as this. Electric bulb is represented like this. An ammeter as this. The voltmeter like this. A switch which is open is represented as this. A switch which is closed is represented like this. A wire joint will be represented like this. Two wires coming to the same point and a node between them. Wire crossing without joint. These are two wires which are crossing without any joint. A galvanometer is represented this with a G. A fuse is represented like this. So these are the electrical components. For them we have decided the symbols. Now let's talk about Ohm's law. What is Ohm's law? Let's discuss. Let us consider a conductor with the resistance R, which is connected in parallel with the voltmeter and in series with the ammeter, and a battery is giving the supply to this conductor. So what happens? This electric current is directly proportional to the potential across the conductor. So watch here, the electric current flowing through a conductor is directly proportional to the potential difference across its ends. So watch here, provided that the physical conditions like temperature, pressure and volume remain constant. So under these conditions like temperature, pressure and volume, when these remain constant, the electric current flowing in the circuit is directly proportional to the potential across the ends of this conductor. So we will write it like I proportional V. The electric current is proportional to the electric potential, or we can write it like V proportional I. The electric potential will be directly proportional to the electric current, vice versa. So watch here, this V proportional I we will take here, and here is a sign of proportionality. Whenever we remove the sign of proportionality, we take a constant, and here the constant is R. We can write it like V is equal to IR, which is the expression for the Ohm's law. So this R is a constant called the resistance of the conductor. So let's define the resistance of the conductor. The factor which opposes the current flowing through a conductor is called the resistance. Now we will get the unit of this resistance. Watch here, from V is equal to IR we can get R is equal to V upon I. So with the help of this we can decide the unit of the resistance. The unit of potential is volt and the unit of current is ampere. So the unit for resistance will be volt upon ampere or volt per ampere. Watch here, the resistance is represented by R. Its unit is volt per ampere or ohm. Ohm is symbolized as this. So watch here, let's draw a VI graph. The graph between the potential and the electric current is a straight line. Watch here, the y-axis is representing the potential difference, the x-axis is representing the electric current. When we draw a graph between V and I, we get a straight line. So the graph between the voltage and current is a straight line. So if we want to find out the resistance from this graph, how to find out the resistance with the help of this graph? Watch here, we have taken 2 points P and Q. we have calculated the electric current between these 2 points P and Q, which is delta I. We have calculated the potential difference between these 2 points, which is delta V. So if we have delta I and delta V, how to find out the resistance? Watch here. The resistance will be equal to delta V upon delta I. This is the expression for the resistance in this case, in the case of a graph, in the case of a VI graph. So let's talk about specific resistance or resistivity. So what is specific resistance or resistivity? Let's discuss. Let us consider a conductor of length L and the cross section A, cross sectional area A. The resistance of this conductor is R. So the resistance of this conductor will be directly proportional to the length of the conductor. Watch here. The resistance of a conductor is directly proportional to the length of the conductor, that is R proportional L. And this resistance will be inversely proportional to the cross-sectional area. Watch here. The resistance of a conductor is inversely proportional to the area of cross-section of the conductor. We can write it like R inversely proportional A. When we combine these two relations, what we get? We get this. Let's combine. Combining these two relations, we get R proportional L upon A. We can see here R is directly proportional to L, but R is inversely proportional to A. So here is a sign of proportionality. You can see whenever we remove the sign of proportionality, we take a constant, and here the constant is rho. This symbol is called rho. So this rho is the specific resistance or resistivity. So this is the expression for the resistance in the terms of specific resistance. Now we will define the specific resistance with the help of this formula. Watch here. Where rho is a constant, rho is spelled as RHO, which is called the specific resistance or resistivity of the conductor. From R is equal to rho L upon A, we can calculate the value of rho, which will be equal to rho is equal to RA upon L. Take this A over here, take this L upon. So the rho is equal to RA upon L. With the help of this formula, we will define the specific resistance or resistivity, that is rho. So let's define. If we take this L as 1, if L is equal to 1, and we take this A as 1, that is A is equal to 1, then what happens? Watch here. Then rho is equal to R. Now we can read it. The resistance of a conductor of unit length and unit cross-sectional area is equal to the specific resistance of the conductor. So watch here. The resistance per unit length per unit cross-sectional area of a conductor is equal to the specific resistance of the conductor. Now we will get the unit of this. Watch here. The specific resistance or the resistivity is represented as rho. The unit of specific resistance is ohm meter. How is it ohm meter? Watch here. The unit for resistance is ohm. The unit of area is meter square, and the unit of length is meter. Area is meter square and length is meter. So 1 meter is cancelled by 1 meter. We get only 1 meter here and becomes ohm meter. The unit of specific resistance becomes ohm meter. Moving ahead with some more about resistors, which is combination of resistors. So how to combine the resistors? Let's discuss. We can combine the resistors in series. We can combine the resistors in parallel. So how to combine them? Let's discuss. First of all, we will discuss about the resistors in series. Okay, watch here. These three resistors are here, R1, R2 and R3. These three resistors are connected in series. When the resistors are connected end to end, then the combination is called the resistors in series. So in case of the resistor in series, we have to learn 2 points. In series combination of the resistors, the current through each resistor remains the same. This current I will flow in all the 3 resistors, and the potential difference across each resistor is different. This potential is divided according to the resistors. The potential difference across each resistor is different. So if we consider the potential across R1 is V1, the potential across R2 is V2, the potential across R3 is V3. Then we can calculate the values of the potentials with the help of Ohm's law. So watch here. The potential difference across R1 is V1 is equal to IR1. We have taken as V1, which is the potential across R1. We have taken as R1, but here we are taking I because I is same for all. So we are not taking I1, we are taking just I because I is same for all. So the potential difference across R1 is V1 is equal to IR1. In the same way, the potential difference across R2 is V2 is equal to IR2. So, and again, the potential difference across R3 is V3 is equal to IR3. These three potentials V1, V2 and V3 comes from this total potential. So this potential will be equal to the sum of this V1, V2 and V3. The sum of these V1, V2 and V3 will give the total potential. So let's calculate the total potential. The total potential difference V is equal to V1 plus V2 plus V3. Now put the values of V1, V2 and V3. Watch here. We have put the value of IR1 as V1, IR2 as V2, IR3 as V3 and IR as V. We will take this I as common in these three terms. So this is here. We have taken I as common within the bracket. There is R1 plus R2 plus R3. This I will be cancelled by that I and we will get R is equal to R1 plus R2 plus R3. This is the net resistance or the total resistance or the equivalent resistance of these three resistors. The equivalent of these three resistors is given as R is equal to R1 plus R2 plus R3. So if there are more than three resistors, if more than three resistors are there in series, then the resultant resistance of those resistors will be given as R is equal to R1 plus R2 plus R3 plus R4 plus R5 and so on. The number of resistors we have, all of the resistors we have to add directly to get the total resistance in case of series combination. So this is the formula or the expression for the net resistance or the resultant resistance in case of series combination. Now let's talk about the resistors in parallel. The resistors in parallel. So how to connect the resistors in parallel? Watch here. This resistance R1, R2 and R3. These three resistors are connected in parallel. How to connect them in parallel? One point of each resistor is connected to one terminal and another ends of each resistor is connected with the another terminal. One with the one terminal and another ends of each resistor to the another terminal. So these three resistors are in parallel. How to find out the resultant in case of parallel combination we will discuss here. In parallel combination of the resistors, we must learn two things. Watch here. The current I is coming from here to these branches. When this current I comes to these branches, it divides into the branches. In this branch the current is I1, in this branch the current is I2, and in the last branch the current is I3. So the current in each and every resistor which is connected in the parallel combination is different. In parallel combination the current is different in each resistor, but the potential is same in each resistor. So watch here, these 2 points we must remember. The potential difference across each resistor remains the same, but the current through each resistor is different. Now the current through R1 will be given as, with the help of Ohm's law, will be I1 is equal to V upon R1. We are taking this V as V, we are not taking V1 because the potential is constant, the potential is same for all the three resistors. So I1 is equal to V upon R1. Now let's talk about the current through R2, which will be given as I2 is equal to V upon R2, and the current through R3 will be given as I3 is equal to V upon R3. The total of these three currents I1, I2 and I3 will be given as the sum of all the electric currents. I is equal to I1 plus I2 plus I3. Now put the values of I1 as V upon R1, the value of I2 as V upon R2, the value of I3 as V upon R3, and the value of I as V upon R. We can take V as common in these three terms. So watch here. This V we have taken as common. So inside that is 1 upon R1 plus 1 upon R2 plus 1 upon R3. Now this V is cancelled by that V, and we have 1 upon R is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. So in case of parallel combination of the resistors, the resultant is given as the sum of reciprocals of the resistors is equal to the reciprocal of the resultant. In case of resistors in parallel, we add the reciprocals of the resistors. So watch here. If there are more than 3 resistors in parallel, then the resultant will be 1 upon R is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3 plus 1 upon R4 plus 1 upon R5 and so on. If more than 3 resistors are then how to calculate the resultant of them? We must add their reciprocals to get the reciprocal of the resultant resistance. So this is the expression for the combination of resistors in parallel. Now let's talk about electric power. We have learned in the class 9th about the mechanical power. That was the rate of doing mechanical work. The rate of doing mechanical work is called the mechanical power. In case of electric power, the rate of doing electrical power is called electric power. Watch here. The rate of doing electrical work is called electric power, and it is given as P is equal to W upon T. As we know that W is equal to VQ from the definition of the electric potential, W is equal to VQ. So we can put the value of W as VQ. So put the value of W as VQ, we will get W as VQ and T as it is. Now watch here. This Q upon T becomes I. From the definition of electric current, Q upon T is equal to I. So we can take this Q upon T as I. So P is equal to VI. This is the expression for the electric power. P is equal to VI. This is okay. Now we will elaborate this P is equal to VI some more. From P is equal to VI, watch here. From the Ohm's law, we know that V is equal to IR. Put the value of V as IR. So we will get V. We have put the value of V as IR into this I as it is. So this becomes P is equal to I into I becomes I square into R. So P is equal to I square R. This is the expression of the power in terms of electric current and resistance. This is okay. Now we will elaborate a little bit more. P is equal to VI. Now elaborate the value of I. From the Ohm's law, we have I is equal to V upon R. Put the value of I as V upon R. So we have this V as it is, and the value of I is V upon R. So this becomes V into V becomes V square. So we have P is equal to V square upon R. This is the formula for the electric power in the terms of potential and resistance. Now let's talk about more. We can conclude that for the different formulae of the electric power, which are P is equal to VI is equal to I square R is equal to V square upon R. These are the formulae for electric power. P is equal to VI is equal to I square R is equal to V square upon R. Okay, now let's talk about some more about this. The unit of the electric power. Watch here. P is equal to VI. The electric power is represented as P. The unit of V is volt, the unit of I is ampere. So the unit of electric power will be volt ampere. This volt ampere is also called watt. Some large units are there which are kilowatt and megawatt. 1 kilowatt is equal to 10 raised to the power 3 watt, and 1 megawatt is equal to 10 raised to the power 6 watt. Now let's talk about the heating effect of electric current. So what is the heating effect? Let's discuss. When the electric current flows through an electric circuit of very high resistance, the electrical energy is dissipated in the form of heat. If the electric current is flowing in very high resistance, then that resistance starts to produce some heat. which is called the heating effect of the electric current. The electrical energy is dissipated in the form of heat from that wire or the resistor. Then we say that this is the heating effect of the electric current. This phenomenon is called heating effect of electric current. This effect is utilized in electric heater, electric iron, etc. We are aware about the electric heater and electric iron. This electric effect, which is heating effect, is utilized in these two devices. So watch here. How to calculate the heat generated? Let's discuss. The amount of heat H produced for the power input P to the circuit within time T will be given as H is equal to P into T. As we know, P is equal to VI from the formula of power. So we can put it P as VI. So the heat generated becomes H is equal to VIT. And as we know, P is equal to V square upon R. So we can put the value of P as V square upon R. So this becomes H is equal to V square upon R into T. One more thing we know, P is equal to I square R. If we put the value P is equal to I square R, then it becomes H is equal to Y square RT. So these are the formulae for the heat generated from a conductor of high resistance. Now let's talk about more about this H is equal to I square RT. This is called Joule's law of heating. We will elaborate this like this. H is equal to I square RT. We can write it like H proportional I square here, H proportional R here, H proportional T here. So the heat produced is directly proportional to the square of the current, to the resistance, and to the time of the current flow. These three relation of proportionality says the Joule's law of heating. So we can conclude that according to Joule's law of heating, the heat produced in a resistor is directly proportional to the square of the electric current, this, the resistance, this, and the time for which the flow of current takes place, this. So this is called Joule's law of heating. See you in the next lecture. Thank you for now.